At more than 25,000 miles per hour, NASA's Orion spacecraft will smash into Earth's atmosphere. Not gently, not slowly. It will hit the air so violently that the molecules in front of it compress and ignite, forming a glowing plasma that wraps the capsule like fire. Temperatures will spike beyond 5,000 degrees Fahrenheit, hotter than molten lava, hotter than volcanic eruptions, and hotter than almost anything humans have ever engineered a vehicle to survive. Inside that firestorm will be 4 astronauts on Artemis II, trusting their lives to a spacecraft designed to do something very strange. It doesn't resist the heat. It lets itself burn. Re-entry is often misunderstood as the final, easy phase of a space mission. Launch looks dramatic, with flames and explosions, but history tells a different story. Some of the most dangerous moments in human spaceflight have happened while coming home. Apollo 13 nearly ended in disaster during re-entry. Space Shuttle Columbia was lost because of damage that only became fatal during atmospheric return. Orion faces an even tougher challenge. Apollo capsules returned from the moon at around 24,600 miles per hour. Orion will re-enter Earth's atmosphere at over 25,000 miles per hour, making it the fastest human re-entry vehicle ever flown. At that speed, air doesn't flow around the spacecraft. It slams into it, creating shockwaves and plasma hot enough to melt steel in seconds. During re-entry, Orion will experience a complete communications blackout. For several minutes, mission control will hear nothing. No data, no voice, just silence. If something goes wrong during that window, there is no fix, no command, and no second chance. That's why Orion's heat shield is not just important, it is everything.
Here's the counterintuitive truth. Orion survives because its heat shield is designed to fail. The material protecting the capsule is meant to burn away, crack, and disintegrate. That destruction is not a flaw, it is the entire strategy. The heat shield uses a material called Avcoat, short for ablative coating. Instead of reflecting heat or absorbing it like ceramic tiles, Avcoat sacrifices itself. As temperatures climb beyond 3,000 degrees Fahrenheit, the surface begins to char and vaporize. Each layer that burns away carries heat with it, pulling energy away from the spacecraft and preventing it from reaching the crew cabin. Orion's heat shield is the largest NASA has ever built. It measures about 16.5 feet across and weighs nearly 2,000 pounds. Beneath that charred outer layer is an aluminum pressure vessel where astronauts sit just a few feet away from plasma hotter than the surface of the sun. Thanks to ablation, the inside of the capsule remains at survivable temperatures. While the outside is being destroyed, the crew is protected. But building this heat shield was far more complicated than it sounds. Apollo-era Avcoat was poured by hand into a honeycomb structure. That process worked in the 1960s, but it wasn't scalable, reliable, or safe for modern deep space missions. For Orion, NASA had to reinvent the manufacturing process entirely. Early versions of the heat shield suffered from cracks, voids, and bonding failures. If even a small section fails during re-entry, heat can penetrate deeper than designed, potentially overwhelming the structure. This problem came to a head during Artemis I. Orion returned safely, but engineers noticed unexpected erosion patterns on the heat shield. Some regions burned away faster than predicted. The spacecraft survived, but it raised an uncomfortable question. If this was uncrewed, would it be acceptable? With astronauts on board for Artemis II, the margin for error shrinks dramatically. NASA didn't ignore the warning. Engineers refined the Avcoat recipe, improved application methods, and enhanced quality control. Thousands of sensors and thermal models were cross-checked against real flight data. Artemis II's heat shield is not the same as Artemis I's. It is stronger, better understood, and more predictable, but it is still designed to burn. That controlled destruction is what makes survival possible.
Another critical factor is Orion's re-entry trajectory. Unlike most spacecraft, Orion uses a skip re-entry profile. Instead of plunging straight into the atmosphere, it dips in, bounces back out briefly, then re-enters again. This maneuver spreads heating over a longer period and reduces peak temperatures. It also allows Orion to fine-tune its landing zone, increasing recovery accuracy in the Pacific Ocean. But skip re-entry adds complexity. Timing, angle, and velocity must be perfect. Too steep and heat loads spike beyond design limits. Too shallow and the spacecraft could skip off the atmosphere entirely. During this phase, Orion's guidance computer and astronauts work together. Artemis II will be the first mission where humans manually test Orion's handling during high-speed re-entry. That makes this flight not just a test of hardware, but of human-machine interaction under extreme conditions. It is one of the reasons Artemis II is considered riskier than Artemis I, despite using the same basic spacecraft. Radiation shielding, parachute deployment, and structural loads all converge during the final minutes of flight. Orion transitions from hypersonic plasma to violent deceleration forces exceeding 8 Gs. Astronauts will feel several times their body weight pressing them into their seats. Then, suddenly, silence gives way to parachutes. First drogue chutes, then massive main parachutes, slowing Orion from hundreds of miles per hour to a survivable splashdown speed. The reason this moment matters so much is simple. Orion is not just a moon capsule. It is the foundation for future deep space missions. The same heat shield technology will protect crews returning from lunar orbit, lunar surface missions, and eventually Mars trajectories. Mars return speeds will be even higher. If Orion can survive 5,000 degrees Fahrenheit today, it proves humanity can push further tomorrow. This is why Orion looks blunt, heavy, and almost old-fashioned. Every curve is shaped by physics. Every material choice is driven by survival. This is not a sleek spacecraft built for aesthetics. It is a shield wrapped around human lives. As Artemis II approaches, Orion's re-entry will be one of the most watched moments in modern spaceflight, not because it looks dramatic, but because it must work perfectly. The heat shield will burn, the capsule will blacken, pieces will fall away into the atmosphere, and that destruction will mean success. If Orion emerges intact from the firestorm, it will prove that NASA's return to deep space is real, repeatable, and sustainable. It will show that humans can leave Earth, travel farther than ever before, and come home safely. And when those parachutes deploy and Orion splashes down, it won't just mark the end of a mission, it will mark the beginning of the Artemis era. If you found this breakdown enlightening, share it with someone who loves spaceflight. Subscribe for more deep dives like this, and follow Rocketry on Facebook for real-time Artemis II updates, breakdowns, and behind-the-scenes space engineering stories.